I'm Angie Lee. This is my third lab report. Here's the introduction. The aim of this lab is to find out the mass of the black hole by observing a star orbiting around it. So how to do that? We first measure the rate of change in momentum and then derive the gravitational force to calculate the mass of the black hole. And I will discuss the physics principles later. The result of my lab is that the mass of the black hole is approximately 1.4 times 10 to the power of 34 kilograms. And here are the physics principles. The first one is Newton's second law. The net force is equal to the rate of change in momentum. And the second one is the net force is equal to the gravitational force. In this lab, we assume that there is only one force, which is the gravitational force between the star and the black hole. And the third one is the net force is equal to the net force in the parallel component plus the net force in the perpendicular component. And the next one is the rate of change in momentum is equal to the rate of change in momentum in the parallel component plus the rate of change in momentum in the perpendicular component. And the last one is the universal law of gravitation. Since mass is a scalar, we only need the magnitude form of this formula. The magnitude of the gravitational force is equal to the gravitational constant times the mass of the star times the mass of the black hole divided by the distance between the star and the black hole to the power of 2. And then let's look at the code and the data. So first I changed the SID into my email address. And then according to the requirement, I changed the mass of the star into 2 times 10 to the power of 30 kilograms. And I changed the delta T into 86,400 seconds. That is the number of seconds in one day. And then for the momentum, I used the velocity times the mass of the star. The changing velocity is final velocity minus initial velocity, and changing momentum is similar. The rate of changing momentum is the changing momentum divided by changing time. And using Newton's second law, the net force is equal to the rate of changing momentum. P hat is equal to the initial momentum divided by its magnitude. So P hat is the direction of the initial momentum. And the rate of changing the magnitude of the momentum is the magnitude of P final minus the magnitude of P initial divided by the rate of change, the change in time. And the rate of change in momentum in the parallel component is equal to d magnitude p dt times p hat. And using the Newton's second law, the net force in the parallel component is equal to the rate of changing momentum in the parallel component. And the rate of changing momentum in the perpendicular component is equal to the rate of changing momentum minus the rate of changing momentum in the parallel component. And using the Newton's second law again, the net force in the perpendicular component is equal to the rate of changing momentum in the perpendicular component. To calculate the mass of the black hole, we use the gravitational force between the star and the black hole. The magnitude of the net force times the distance between the black hole and the star to the power of 2 divided by the gravitational constant times the mass of the star. And we print the mass of the black hole. Here I change the value of the arrow scale to make the arrows and the trajectory visible. Those arrows represent the net force and its components. And then we run this program. We can see the trajectory and the arrows, and the yellow star and the black hole, and the masses of the black hole are printed here. I put all the data into a Google Sheet and take the average of them, and I get 1.4 times 10 to the power of 34. That is the mass of the black hole. And back to the PowerPoint. For the what does it mean question, the net force is equal to the rate of change of momentum. So they are equal in value. However, they're different in measurement. We cannot directly measure the net force. However, we can measure the rate of change of momentum because we know the velocity of the star and the mass of the star. That is how we did, uh, how we calculated in our code. And for the what if question, since the motion of the star remains the same, the gravitational force between the star and the black hole is the same, and the distance between the star and the black hole is the same too. And also the gravitational constant and the mass of star remain unchanged. So the mass of the new black hole is the same as the previous one. Therefore, there is no difference. For the conclusion part, the mass of the black hole is about 1.4 times 10 to the power of 34 kilograms. And for the improvement part, I can change the value of delta t, since in this lab we assume that there are 86,400 seconds in one day. In reality, that is not the case. We can make it more accurate. And thank you.